In this video, we will explore the fundamentals of a widely used encryption algorithm known as AES. To begin, let's first ask, what is AES? AES stands for Advanced Encryption Standard and is an algorithm that encrypts plain text and outputs ciphertext. Before we get into the algorithm itself, let's first discuss its historical context. In 1997, the National Institute of Standards and Technology saw a need to replace the current standard encryption algorithm known as DES. DES, which stands for Data Encryption Standard, used a 56-bit key, which proved to be too small as it was made public that it could be broken in as little as 22 hours. So a competition was held among various members in this field to come up with a better form of encryption. Two Belgian cryptographers by the name of Vincent Rijman and Joan Damon were declared the winners for their algorithm that is now known as AES. The algorithm was published in 1998 and chosen as the new standard in encryption in the year 2000. Before we get into the specifics of the algorithm, it is important to clarify some key terms that we'll use when describing AES. The first is a key. Similar to a key to open a lockbox, a key is a set of instructions that tells either the sender or receiver how many of what operations are needed to either encode or decode the message. In the case of AES, both the sender and receiver have the same key. AES has three key sizes. The size of the key dictates how many times the block matrix is shifted. A 128-bit key executes 10 rounds of encryption, a 196-bit key, 12 rounds, and a 256-bit key would do 14 rounds of execution. The larger the key size, the longer it takes to encrypt and decrypt the data, but is more secure with the increase in key size. All key sizes are considered secure. In order to crack the 128-bit key, you would have to process 38 trillion terabytes of data, which is more data than is stored on all the computers in the world in 2016. This would take billions of years on current hardware. The only way to crack AES is to obtain the key in some way. There is no known practical way to crack these keys. The next term is a block cipher. A block cipher is an encryption method that takes an input, a block, of plain text, and encrypts the text by shifting the bytes stored within a block a number of times. Take the following key for example. In plain text we have A, B, C, D, E, F, and in ciphertext we would have F, A, B, C, D, E. The word face in ciphertext is E, F, B, D, where the block cipher is right shifted by 1. You'll notice that the letters in the ciphertext row are in the same order as plain text, but are right shifted by 1. The output EFBD of this operation is known as ciphertext. The ciphertext is the encrypted data that results from the block cipher operation and can be sent over a network with confidence in confidentiality. The size of the block in AES is 128 bits. Now that we understand what a key, block cipher, and ciphertext is, we can discuss the steps of the AES algorithm. Remember that AES takes in plain text and outputs ciphertext. Alice wants to send a message to Bob without a nefarious person reading it, so the message should be intercepted. AES assumes that both Alice and Bob have the same shared key. AES uses a 128-bit block, which is 16 bytes. These bytes are written as a 4x4 matrix, where each cell in the matrix contains 1 byte. At each round, the following 3 operations are performed. All of these steps are performed in such a way that they are reversible so that the data can be decrypted. First, the first step is a substitution step where each cell in the block matrix is replaced with a corresponding byte from a substitution matrix. The second step is a shifting step where rows of the block matrix are cyclically shifted based on an offset that is determined by the location of the row in the matrix. These shifts are always by power of 2. And third is a mixing step, where the columns of the block matrix are combined using an invertible linear transformation formula. These 3 steps are iterated each time and are considered one round of encryption. After the final round, we perform the following step. And it's an additional step where a subkey, which is derived from the main encryption key round, is combined with each cell of the block matrix. This step is only used in the final round of the encryption process. In order to decrypt the data, these exact steps are performed again, but only in reverse order. To explain the algorithm in even greater detail, we will step through the implementation of the algorithm.
The steps in AES are actually fairly simple. So I'm going to show the main steps in AES and how they work. This is our round function. This is repeated multiple times for every chunk of data, a chunk being a 4x4 array of bytes, so 16 bytes. And then the bytes undergo subbytes, shift rows, and then mixed columns. And these are just ways of moving around the data to obfuscate them. So the subbytes simply substitutes the values in the matrix for values of sbox, which is a array of length 256 that has a value for every possible byte. So if the value in the matrix was 0, it'll become 63, and it's as simple as that. And then shift rows just moves each row by a certain amount, and this is actually dependent on which row it's at. So the first row in the matrix won't actually be shifted at all. The first one, or the second one, will be shifted by 1. The third one will be shifted by 2, and the fourth one will be shifted by 3. And then mixed columns is called. And this is probably the most complicated. It's basically just some fairly simple algebra done in a fancy way that can be undone. And it combines multiple values in the array into one single value, and then sets that back into the array. And that is essentially how encryption works. There's also add round key, which XORs the values in the round key with the matrix. And then to decrypt, it is the same steps done in reverse. So that's inverse mixed columns, inverse shift rows, and inverse subbytes. So for example, for inverse subbytes, when you put in 63, you'd get 0 instead of putting in 0 to get 63. And that's encryption and decryption. Alright, now I'm going to show you a little example of what this would look like on an image. So this will actually encrypt the whole image by one round and then display it, and then go on to the next round. And this does for 10 rounds, and then tries to decrypt it. And so as you can see, it's all noise. Without the round key, would be no way to recover the data. And it's hit 10 rounds, so that's fully encrypted, and then it starts decrypting. And hopefully we'll have a little red panda at the end. And alright, it worked. We recovered the data, and we didn't lose the red panda.